Record. Welcome. So, today we're going to talk probability. We're going to talk probability today and next time for the reason that the big picture of being able to do statistics. What is statistics? That is learning from data in an intelligent way. The intelligence is very much linked to the concept of randomness and probability. To be able to know what we can use data for, both in an optimal way and not too much. Probability is the tool for us to be considering. So the plan is the following. Random variable distribution, specific distribution, one of them at least I think you've met before in life, the binomial. But we're gonna game and play also. Are you ready? Let's begin all right away because I have a little check question on you in the beginning. I still warn you, I have the power to exclude you from the game if you don't behave. So I think I'm about being ready. Is that who we are? Okay, let's start. 8 questions today. 10 seconds. Now I actually did a mistake here, since you were not going to have this one now. Anyway, here you go. If you do this, even in 30 seconds, I'm impressed. No, I'm not full screening for streaming reasons. Sorry. Not too bad, actually, before I actually taught you what a density function is. So, quite well. Let me teach you what a density function is. Because that's the first topic of this morning. Afternoon, it's not mornings, I know. Random variables and their density function. Random variables. Well, that's the mathematical concept of talking about events that hasn't happened yet. Could be a dice throw, the number of 6s in 10 dice throws. Measurements of a randomly selected patient, glucose level in a blood sample from a randomly selected diabetes patient, or whatever. This is the framework we have to talk about randomness in nature and data. Nature, randomness in nature and data. Now the outcomes of data basically can be put into two different types, and also the nature beneath it, namely discrete type outcomes and continuous outcomes. Discrete events, systems, is like throwing a dice, throwing a coin. There can be 2, there can be 6 possible outcomes. They are not only discrete, they are also countable. Question? Mic is dead. Is it better now? It was enough just to move it a little bit like that. Thank you. Thank you, thank you. Sådan der. Så kører vi det igen der. Tak. Thank you. When I start mixing languages, because I get stressed. Let's try to stick to the English then and cool down. The other thing is sometimes what we measure or record, the data we have, comes from real quantitative phenomenon, like the concentration of alcohol or glucose in our blood. That's by nature a quantitative continuous phenomenon, right? So mathematically, we need to split those two into two different kinds of approaches. The discrete approach and the continuous approach. That's why we have today and next time to cover the probability basics of those two settings. In the discrete world, we have to add things up. In the continuous world, we integrate continuous functions. That's the difference. So here's a bit of notation. We talk about either capital X, or sometimes we emphasize that there are actually n different of them. Then when we have the data, we will talk about the actual sample that we are having. We use small x, or maybe small x1 up to xn if we have a sample consisting of n observations. It's not going to be a big issue for us when working with this. It's just like a declaration of notation in a way. Let's get going with a bit of playing around. Let's try to simulate some randomness by the computer. We'll get more back to the simulation issue. But the really nice thing about R and the computer is that can help us understand randomness, because it can actually do pseudo-random numbers to us. So here's we use R as kind of pedagogical learning instrument. Let's see. Let's try here. Now I'm in R Studio. It has a sample function that can sample at random. I had a 6, I had a 4. This is one throw with a dice, right? Great, great game already there. Now if we want a bit more fun game, we can do like this. Look at this, I sampled actually now 30 throws. I simulated 30 throws with a dice. I could look at the outcomes, or I could tabulate the outcomes here, right? Here is kind of a frequency distribution actually already, an empirical frequency distribution. We could plot that. Look at what I've added to the plot now. I've added some red bars. Can you recognize those red bars? I call it the PDF, the probability density function. That's the fancy name for the number 1/6 in this case, because that's the underlying long-term probability for getting a 1 and also a 2 and also a 3. That's the 1/6. So that's what we're formally defining in the slides now. And in a way, the idea is to be able to talk about these issues without actually doing the thing. That's the concept of modeling and putting things into a mathematical framework, that we can deal with it conceptually in the computer. So that's the density function, nothing but the probabilities of the individual outcomes. In the discrete world today, this is the definition of the density function. So for the dice, we saw that already. For the fair dice, because we are going to be able to work with cases where it's maybe not fair, the fair dice is 1/6 for each. If you want to be a bit of mathematical, for the density, we have mathematically any function which is positive and adds up to 1, which means they're all smaller than 1, those potential probabilities. They will be, that could be a density function. So it's kind of, this is a bit of abstract definition, but it's just to illustrate that this mathematical framework is pretty general. It can handle very different kinds of probability density functions, the framework we are introducing here. For instance, the one we already met. Now we're going to use this for statistics. So even though it's actually a probability day, I am going to relate it to what the purpose of this probability thing is in a statistical course, because you can take a complete class in probability, 2405, given by a brilliant teacher, Bo Friis Nielsen. You can learn about probability. Probability itself is a very important tool as an engineer, as a modeling tool for all sorts of phenomenon. In nature, in biology, in computers, wherever, in games, of course, in stock markets. I mean, probability models and being able to work with those are in its own right a very important mathematical modeling tool, an engineering relevant tool. In our course, we are just giving you the very basics to be able to do statistics, the basics of statistics. But statistics and probability go hand in hand. But if you want to be very formal about it, it's two different things. Probability is part of mathematics. Statistics is trying to learn about data, which is not pure mathematics, actually. It's using mathematics and probability, but it's something more. So, here is actually the one that I just did. I was a bit ahead of myself. This is just a slide showing you what I just did. So let me go rapid here. And then it's quite easy also. Look at the only difference now to what I just did is that instead of having 1/6, 1/6, I could put this as actually, you see, I repeat the number 1/7 5 times, and then I put 2/7 at the end, so I have it adds up to 1. That could be the unfair. Let's not do it in R now, but let's do this little exercise here, since I already did the Kahoot on densities with you. So let's do a little questionnaire here and see if we can solve this. For this unfair probability density distribution, what's the probability to get a 4? Also, small f taken in 4. Well, it's not the most difficult question you'll meet in this course. Any who would like to say the word? 1/7. Thank you. What's the probability to get a 5 or a 6? Now we are skipping all the basics of these set theory and probability basic theory and just assume that we can all use common sense here without doing all the theory about it. What's the probability to get 5 or 6? Yes? I'm sorry? 3/7. Do we agree? Yes. 1 from 5 and 2 from 6. So that's the adding up principle. Like that. What's the probability to get less than 3? Yes? 2/7. Less than 3 would be these two, which correctly is 2/7. Common sense rules, right. That was the first part. And we did the Kahoot already, so by mistake, so let's skip that now.